The speaker, Dr. Christian Jepsen, right, from KIAS, and he's going to talk about the physics of hierarchical systems this time.
Yeah. So thank you so much for the invitation. This is actually my first time at Sogang University. I was very pleasantly surprised to discover it's quite easy to get here. You know, we're basically next door neighbors, right? It's a direct ride on the line 6. Yeah, and so let's see if I can't. I'll try to get you all started off to a good weekend with this talk. Where then I'll first try to explain what on earth I mean by this term hierarchical systems, right? So even the talk title itself might seem a bit bizarre. So the idea is that we're going to look at systems that aren't sort of, or where the organizing principle isn't sort of the familiar standard linear way that you might rank things. Instead, they'll be organized in sort of a different way, which is what I refer to as hierarchical, right? And so if you just try to think of having some spin sites that can couple to each other, then what we're going to be looking at is a specific kind of all-to-all coupling. So in general, if everything can couple to everything, it's a mess. You can't do anything. But this is a sort of a subset of generic couplings that are so specialized and have actually a lot of symmetry that you can do some things analytically. And so the topology of this kind of hierarchical ordering is a bit weird. But so let me try to explain it just with sort of an analogy. Right, and so this tree of life is actually going to be kind of a useful metaphor. So the point is that, like, in some sense, like all life that we know of, right, all life on Earth is in some way related to each other, right? If you go far enough back, there's some common ancestor, right? And the way that sort of the relationship between life isn't linear. That is what I would call this kind of hierarchical with the weird topology. Right? Because, for example, all your siblings, right? You're all equally related. So in that sense, it's like every point in a ball is a center of that ball, right? And all of your siblings have the same shared amount of DNA with all of your cousins. Okay. But so to make this analogy more precise, we should imagine some life where each generation has the same amount of offspring. And of course, if you think of like a biological systems, that would be some like very specialized, like, kind of toy model where every generation has the same number of offspring. But the point is just that there's some cases where this kind of lamppost can be a better toy model than our more familiar spherical cows we use in physics. So here's sort of the rough plan. So I'll start by explaining these kind of theories a little bit. I'm giving you a concrete example that will hopefully help demystify a bit this kind of weird description I've given so far. And after that, the goal then is to explain how you can sometimes have different, have systems that can sort of interpolate between the different kinds of order, right? It's like in real life, things aren't often either black or white, right? They're very often shades of gray. Okay? And then I'll get to this promised, maybe you might have seen in the abstract, like how there's actually been some experimental measurements of systems of the kind that we'll be discussing today. And then this might seem a bit weird that I'm sort of going to try to motivate it sort of after the fact by talking about where you might see its occurrence, right? But this, to me, felt the more honest way of doing things, right? Like sometimes you first identify a phenomenon, and then you see where that phenomenon is present or not present. Even though, of course, sometimes you write papers the other way around, but first you say that it's present, and therefore it's worth studying. Okay, and then finally, this is sort of the slightly more speculative part. This is where it's sort of with the more high energy theory flavor to it, where I'll talk about sort of kind of like hierarchical inspired, like sort of string theory-esque theories. But okay, I think that'll be easy to explain once we get there. So let's make our way. We have some ground to cover. So starting now with just explaining what are these theories, and maybe can I just give you a concrete example so you know what we're dealing with. Okay, so model we'll start on is this model called the Dyson hierarchical model that was put forward by Freeman Dyson in 1968. Okay, so indeed, as mentioned, it's kind of all-to-all coupling between some spin degrees of freedom. We'll just take them to be C2 valued. Okay, and now the idea is that we have spins that are grouped into clusters. Okay, and all the clusters have some specific coupling amongst them. Okay, then additionally we have clusters of clusters. Right, where then across clusters there's an interaction, and then we have clusters of clusters of clusters, and so on, however many layers you want. And the cluster size, you can take it to be anything, right? If you write down a model, but for concreteness, we'll take it to be 2. So let's just try to write down some Hamiltonian just to make it slightly more precise, right? So here then is the idea of the clusters, right? We have pairs of spins that couple with some coupling G1, okay? And then the spins in one cluster couple to their neighbors with some other coupling G2, right? And then some coupling G3 if they're not on the same sort of second layer blob, right? And then, of course, third layer blobs, they might couple to each other. And why is this, at least from a theorist perspective, why is this a nice model to study? Well, the idea is that if you imagine you perform an RG step, right? Like you integrate out half the degrees of freedom, right? And then you get a new system, and then you rewrite the couplings in such a way that they have the same form you started with, right? This is something that might be very familiar from like the Isaac chain, right? And what's so special about this kind of model is that you might almost be able to intuit it already, right? But the point is, if you integrate out half the degrees of freedom, right, the couplings between the remaining degrees of freedom will have this same form as you started out with. You'll again have the same kind of hierarchical pattern, right? That simply follows from the symmetry of the model, right? In some sense, this is an extremely symmetrical model, right? Because you'll notice that if you interchange any pairs of spin in a blob, right, the total energy is going to be unchanged, right? But you can also interchange blobs at the second level and at the next level. So you actually have like a very large sort of permutation symmetry acting at each level. And this is the C2 case, right? But you can imagine having larger cluster sizes. Okay? And so Danielson's motivation for writing this down was just he wanted to like rigorously, he's a very Freeman Dyson, he was a very mathematically minded guy. He liked to have like rigorous proofs. So what he wanted to do with this model was to just have some model besides the sort of garden variety local nearest neighbor coupling systems you study. He wanted to have a different kind of model and rigorously establish that you had a phase transition. That was his goal. So that's why he picked this special baryssymmetric theory. Okay. So in the RG language, right, you can flow to a trivial, like a free fixed point, or there's a non-trivial interacting free point. And if any of you are familiar with the long-range Ising model, this is a very similar scenario, because it's actually, you don't just have one non-trivial interacting fixed point. You actually have sort of a continuous family of them. But then the story you probably are familiar with from the Ising model, right, is that what happens when you're at the phase transition, right, is that's the point where you start to see universality, right, where you get long-range interaction, so the microscopic details don't really matter, and you can see the exact same critical data, whether you're working in a continuum quantum field theory or whether you're working on a lattice, right? But this is like or experimentally, right? This is like if you measure the critical exponents, right? You look at, say, water near the critical point, right? Then you will measure the same values for water as you would for methane or for ethane, for argon, for xenon, right? That's a power of universality. So the point is, universality also, yes.
Is there integrable structure in Dyson model?
Well, I would say it hasn't been solved, but I'm tempted to say it could be. But then again, I would compare it to the long-range Ising model. So I think the absence of locality is what makes it is why no one has solved it, which of course is not the same as saying it cannot be. But so I would say it is as solvable or unsolvable as the long-range Ising model. Okay, yeah, so the continuum limit, right? So because I was talking about how you have this phenomenon, universality, lattice theory, continuous theory describe the same. What is the continuum limit of this kind of hierarchical pattern? Okay. And one way to think about it is to think about it as the boundary of a tree, right? The same sort of similar to the tree we had in this biological analogy earlier, right? And so if you generalize, this tree is drawn for the same case as before with a 2 cluster size, right? So the point is, if you think of the boundary here, you can think of as clusters at different levels, right? Like this pair being the smallest cluster, then the second layer of clusters, and so on. Okay? And so there is a formal sort of mathematical sense in which you really can take the continuum limit, and the individual points will be basically, if you pick any point here, then you can have paths that go out to the boundary. And each of those paths or each of those boundary points infinitely far away will then give you sort of a value of your boundary variable, which is a continuous variable, so that you can even define an integration measure. Okay, so this is, it's useful to introduce sort of a notion of a hierarchical distance. And so this is sort of a bit related to how I was saying the topology is a bit different. You can sort of think of it as we're looking at distances in sort of a different way than we do normally in physics. So the idea is that if you have two vertices on the tree, then the distance, you can just measure how many edges are they separated from each other, okay? And so the idea is you can do that for the finite tree, right? And then let me go back again. So if we imagine this as a cutoff tree, right? Then if we take two boundary points, which I would say are like in the same cluster in the original language, right? Then you have to move two edges to go from one boundary point to the other. And then to get to the next one, you have to go 4 edges, right? So in some sense, the tree itself provides sort of a natural way of measuring distances between boundary points that behaves a bit different from our usual notion of distance. And actually, I can't resist pointing out, since we are in Korea, right, that this is actually kind of used in the Korean language, because my understanding is, right, the word for uncle is samchun, right, which relates to the fact that you have to go, if you 2 steps back to your grandparents, 1 step down to your uncle, right? And cousin is sachun, because you have to take 4 steps, right? So actually, this is something that might be a little more familiar to all of you. Okay. And so this measure, it also works in the infinite limit. The way I've described it, of course, the distance between points becomes infinite as the tree becomes infinitely long. But you can introduce some proportionality, some constant in front, which you scale with your cutoff in such a way that you get a finite limit. So that's possible. And this measure will be defined in the continuum limit. Okay. And then, yeah, my apologies to the phenomenologist. I couldn't resist putting an ADS CFT comment, because this kind of tree picture, right, it sort of naturally lends itself to holography, right, because you have sort of a bulk structure and you have a boundary structure. So this is, I might say, is like the simplest possible version of ADS you could imagine. So what this physicist Sabrodin, he showed in the late 80s, was basically that if you write down like sort of the most natural theory you can on the tree graph, which is just you take what's called the graph Laplacian, right? Which is just, it means that the graph Laplacian acting on a point just gives you the differences between all the neighboring points. So what he showed was that if you have this action on the tree and you put sources at the boundary of the tree, then you get the same, then all the correlators will give you the same as if you had an action just to, those same source terms on the boundary, but then an action now defined only on the boundary, where then this is kind of you can think of this almost as like a non-local kinetic term, right? Where correlations are measured now according to how far away they're separated by this ultrametric distance I introduced to you, right? So this is kind of like, in hindsight, this can be reinterpreted and written in a way that's very similar to sort of the standard ADS CFT dictionary.
Oh,
Yeah, please.
in the perfect equation, you have the Laplace, right?
This one.
Yeah, this is the second derivative, but on the right-hand side, we just computed the difference.
That's right. That's yeah. It's because this is what's called the graph Laplacian.
Is it different?
Oh. Yeah, so it really is defined this way. And one way to sort of justify it is that sometimes people have tried to introduce the Dirac, sort of the Dirac operator on the tree, which is what we would think of as a single derivative. And so there it works the way that you have vertices, but then you also have degrees of freedom living on the edges. So then the sort of the one derivative, the Dirac operator, would then take the difference between edge and vertex, right? And so in that sense, this is sort of a double derivative, because you go from vertex to edge to the next vertex. But you can just take this as a definition of like how, like this definition existed before Sabrodin, right? This was mathematician introduced this notion of graph Laplacian. Yeah, so I use the word ADS CFT, but what on earth are the kind of CFTs we're dealing with here? So there was actually this guy Melzer. This was actually his PhD thesis. He was a PhD student at Chicago, where he wrote down axioms for them. The term he used was non-Archimedean conformal field theories. Okay. So what he did, this was also, there were some mathematical reasons that made it more easy for him. He specifically took the cluster size, which I've called P to be prime. The upshot for our purposes is that these p-adic ADS CFTs, in some sense, you do have a scale invariance, right? Like, I hope that maybe makes sense a little bit from like the starting RG picture we had. You can imagine you can perform a rescaling of these trees, right? You can sort of imagine making them larger or smaller. So the idea is that in addition to having translational invariance, right? Because that's like the tree itself as a graph, right? Each point is sort of isomorphic to every other, right? No point sort of stands out as special. So that's translational invariance. You also have scale invariance. And then there is a notion of a special conformal transformation. So the point really I just want to make is that this usual story that we're familiar with from standard lattice model, standard CFTs, right? It's at a renormalization group fixed point, right? you necessarily have scale invariance, right? Because you're at the point where your RG transformations no longer change the system, right? And then what usually happens is that you get this enhancement into conformal symmetry because you pick up this extra special conformal symmetry, right? That's sort of this kind of miracle that happens, which gives you universality. My point is that there is also now a notion of special conformal transformations. So there is a kind of symmetry enhancement to be expected at these hierarchical fixed points, okay? And so also this is really stated, yeah, this was popular with the Russians, I guess, because some of it has a very mathematical flavor, that like the p-adic QFTs describe the critical behavior of these hierarchical lattice models. Okay, so basically you can define hierarchical QFTs and RG flows, okay? And so just to clarify, right, the quantum fields themselves, they're still real valued, right? It's just that their arguments sit on the boundary of this tree. So it's the argument that's this sort of weird, unusual continuum variable, okay? And a consequence of the fact that the field and its argument, they don't live in the same space. So you can't actually take a derivative. And a consequence of this is that the kinetic term is non-local, okay? So you don't have wave function renormalization. And then the RG transformations, you can actually perform them, not just so the RG I showed you at the beginning was sort of position space, right? Where you're integrating out half of the sites on this sort of hierarchical structure. You can actually, there does exist a kind of momentum space. And it turns out, this is sort of mathematical fact, right? But the momentum space is also is the same space, right? It's kind of, if you Fourier transform a real valued function, the Fourier transform is also real, right? That doesn't always happen, right? If, for example, if you have a function defined on the integers, right? The dual is going to be the circle, right? This is just like the Boolean zone if you work in a lattice system, right? So okay, but so yeah, the fact is even in the continuum limit, these RG transformations remain discrete, right? That's related to this norm I introduced, this sort of ultrametric norm I introduced, right? Even when you take the continuum limit, that norm is still discrete. Okay, and so these are just rough facts, and we won't be talking too much about this model. So I'll move on to something more concrete. But let me just take this like the final step, right? And say that if you really wanted to, you could write down like a 5 to the 4th theory or an ON model defined in this weird hierarchical setting. Okay, and then the kinetic term is similar to what we saw in this subordinates version of ADS CFT, right? It's kind of a bilocal kinetic term. But if you Fourier transform this into momentum space, right? Then this thing becomes just the power of k. Look. So the point is that this S you can think of is basically just telling you how much what power you weigh by momentum space. So usually, right, in a local theory, we take the power of momentum to be 2. But the point is, in this case, because the kinetic term remains always non-local, 2 doesn't really stand out as being special. This is what I mentioned about how you really have a theory, like a continuum of fixed points. And this is the same thing that happens in the long-range Ising model, which is basically when you integrate still over the real values.
You're using 2-dimension theory or general dimension?
Yeah, so the notion of dimensionality is a bit weird in this case. So I should say that it's not a perfectly analogous, but there is a notion in which you can have higher dimensions on this tree. So I didn't get into it just for simplicity, but yeah, there is a notion of higher dimensions. And actually, if you introduce that notion, then you can write this thing down in a way that's much more similar to the familiar 5 to the 4 theory. Because in some sense, this spectral parameter, you could say that the power you weigh things with in momentum space is a little bit related. It's kind of like when you do dimensional regularization for renormalization group flows. Like one way to think about the dimensional regularization is basically that it's like you have a matching between the power of momentum and the number of dimensions. So you could imagine that instead of like doing dim-reg, where you change the number of dimensions, you change the power of momentum. So that's sort of an equivalent way of doing dim-reg. So that's what's more natural in this setting. But okay, the upshot, what I really just wanted to say is that you can, as you do for standard real quantum field theories, right? Like, interacting quantum field theories, they're hard to deal with, but sometimes you can take some perturbative limits, right? So you can work out a kind of epsilon expansion, and you can compute CFT observables, order by order in this epsilon expansion. And actually, you can also solve it using the same trick that works for real theories, which is this Hubbard-Stoyanovich transform, right? It's a trick for solving the theory at large n.
Just a question to understand. So that's simple. The absolute value of x minus y, and with the subscript key. Yeah. That does it mean that x and y are living on the boundary of this tree?
Yes.
And x minus y absolute value is the distance defined in the graph diagram.
Yeah,
And then the subscript p means that the cluster size for this case is p.
that's right.
And
Exactly.
then what is the, how can I understand the absolute value of k? Now you have just one number there, then what is k distance between k and 1?
Well,
Then how can I define? Now I can understand now I know how to understand x minus y. Or how should I understand k? Just k with absolute value.
yeah. Well, one way to think about it is you can think of it as k minus 0.
So 0 is to specify somewhere on this.
Yeah, I mean, because you have translational symmetry, it doesn't matter quite too much. But it's actually the same. Like, this is literally what would happen if you Fourier transform over the. Okay, I understand your comment. I haven't actually defined. I defined this only in terms of differences. So there is a definition which I didn't want to give. I can give it when p is prime. So okay, since you asked, I'm just going to tell. There is an answer. There is a way to interpret this, which is that basically that was probably me. No, the point is, yeah. So actually, there is a definition. If you can define, so let me take the prime case where there's a rigorous mathematical definition. Okay, if you have any let's just take a rational number, right? If you have any rational number, you can write this down as some prime powers. Some other prime powers. And so then if you take it with respect to some fixed norm p prime, then basically, let me put minuses here. Oh, let me just get rid of the denominator, right? We can take these to be negative or positive. Then it's just you take that given prime and then you take minus. So the idea is if you take, for example, 27, then it's 3-adic, no, this is also called, yeah, so the automatic norm with cluster size 3 becomes 1/27. And if there are other prime factors, so let's say 54, for example, we multiply this by 2, then this one just ignores it. So there is a definition, but this really is equivalent to what I showed you on the graph, right? Like it really can be shown to be equivalent and taking like 0 as the reference point. But okay, we won't actually need this. So yeah, so let me not distract you any further. So my object here is just, you can solve the model at large n, you can solve it at small epsilon, and you can check that the two expansions, if you take the double limit, they match with each other, they agree, right? So it's kind of like the situation is very similar to the usual one, right? We have interacting fixed points, they're hard to study, we can study them in some limits, the limits agree in the regions of overlap.
Yeah, question.
Yeah.
In second equation, if we perform the Fourier transformation, yeah. So would you go can you go back to the page 7? Or no, maybe page 8 or yeah. And in the last equation we have a relationship between the which said that the distance is proportional to some power p, right?
Yeah.
So is this relation related to that kind of action in the page 12? So yeah, in the page 12 we have performed the Fourier transformation to transform the x minus y into the absolute value of k, right?
Right.
And I think this relation looks kind of similar to that one you have shown in the page 8, right? And that one. So are they related or are they just completely independent ones?
Yeah, it is. I'm using the same norm as this is using what you would get when you take this infinite tree limit of the other definition. So this is, yes, indeed, when you are computing this, indeed, this distance here is itself. This is what I mentioned with it's discrete. It's like p raised to some integer power, right? So when you actually perform this integral at the end of the day, what you end up getting is a bunch of geometric series. Like it's written as an integral, right? Mathematicians consider it an integral as well, but like for practical purposes, when you compute it, you end up actually carrying out infinite sums, indeed, and then they tend to become geometric because you're summing over p raised to powers. That's right. All right, so with that, yeah, let's try to get slightly more down to earth again. So I'm going to try now to write down a very simple model that interpolates between hierarchical and linear order, okay? And in interpolating between them, it'll pass through a regime that has no kind of order, okay? And this model I'll write down is the one where we'll look at like people actually trying to create it in a lab, okay? So the type of model we'll consider now is so you can think of it as a kind of spin chain with like long range couplings, right? And I've written it down now, this sort of coupling constants as a function of the distance, right? So we're looking at translationally invariant systems with some like C2 degrees of freedom, okay? And again, you know, for like finite systems, right, we can perform the finite Fourier transform. So that's just what's done in this step, okay? And so I'm going to now present two reference points, right? Because I'm saying it's interpolating between the two kinds of orders. So I'll first define the two models that like clearly by definition have that order, and then finally we'll show some plots that compares this model to the other, the model, the interpolating model to our reference point. So the local reference point, now it's just sine to a power, right? And the sine to a power is really just, you know, the sign is because we're on a finite system, right? So this really is just like the local case where you have momentum raised to a power. Right, so specifically, you can take s equals to -2. That's the standard local thing. You get nearest neighbor coupling. Okay, so deep negative s means local regime. Okay, and then as s becomes less and less negative and positive, then you move into sort of a more long range area. Okay, so it's roughly this is a power law behavior. So this is the local reference point. Okay, now here comes the hierarchical reference point. So now we use this sort of power of 2 norm. So one way of thinking about it, yeah, this is what I was talking about, right? You divide by the largest power of the given cluster size that divides the number. This might be the easiest way to understand what's going on, might just be to look at this figure. So the idea is that if we label the points, right, and we're taking them to be a power, the total points would be a power of 2, that will make our life simpler. So the point, each point is sort of coupled strongly to its farthest neighbor, right, because they're separated by a large power of 2. And then here they're separated by a smaller power of 2, so the coupling is slightly weaker. And then here the difference is not a power 2, so there's very little coupling. And another way of thinking about it is actually that there exists this map called the monomap, which is basically just you take the binary expression and you flip the digits. So if you do this, then the ones that are separated by a big power of 2 are now transformed next to each other. So performing this monomap, now instead the sort of correlations now become monotonic if you plot them. And so now the interpolating model, this one has a sparse coupling pattern. Okay? So now you're coupling only, the idea is compared to this one I showed you, the hierarchical, right? This is an all-to-all. So you have some coupling, even coupling if there's no power of 2, there's still some remaining coupling. In this one, you're only coupling powers of 2. Okay? So in that sense, it's not an all-to-all coupling. It is sparse, right? Most of the spin pairs don't couple together. But the idea is that as you vary this number s, if s is negative, then you're coupling things spaced by a small power of 2, right? Which means ultimately you're coupling the nearest neighbor. Whereas if you take a large positive s, then it's the farthest powers of 2, which is the ones that have, you know, the small cluster size 2 norm. Okay. So now let's look at the Green's function of the different regimes, right? Just to see the interpolation. And I mean, you know, it's not surprising from the way it's written down. Like it's kind of obvious that it has to interpolate between them. And so the ones in the negative regime, right, we see that the sparse coupling pattern is very close, right, to our sort of standard local reference point. Okay, but as we take this s and we increase it, right, then the sparse pattern gets sort of more and more distinct from this power law pattern we're comparing it with. But at the same time, it starts approaching more and more this kind of non-local, this kind of hierarchical coupling pattern we have, right? And you'll notice that the monomap has been taken, right, along the x-axis, right? So it's like taking this monomap is what now makes it monotonic or almost monotonic, right? So the point is, as we're abandoning the local regime or the linear regime, we enter the hierarchical regime. Okay, and another way to compare this is you can look at continuum limits, right? So basically, it turns out, right, that like, you know, lattice models don't always have a continuum description, right? And the point is, as we vary s, the model will change from having a continuum limit in terms of standard real numbers versus a continuum limit in terms of these like tree boundaries. Okay, we don't have biggest results for the continuity ranges, but roughly it seems like s less than a half or greater than a half is when you get this kind of continuity. So you can kind of see if when you try to take a large system limit in the case when s is positive, right, compared to the standard, the power law, the linear coupling, right, you get this spiky thing, and then as you take s more and more negative, you start to get something that looked like it might have a continuous limit, right? Like some of them clearly are discontinuous if you try to take the system size to infinity. And conversely, right, like if we now compare to the hierarchical model, right, then the continuum limit instead goes away when we go to S negative. Okay. So let's see about this promised experimental realization. So after the model came out, there was this paper where they proposed how you might actually measure it in a cold atom lab. Okay. And the model built on an earlier proposal that's more generic for how you can custom tailor couplings in translational invariant systems by implementing them in an optical cavity. Okay. And then the first mentioned authors, they also provided a bit more motivation for why it might be worthwhile to study them. And basically their punchline is that to really see chaotic behavior, which you can think of, for example, as looking at when you get fast scrambling, or you can look at the level statistics. The point is to get things that are chaotic, you shouldn't have any kind of order, neither linear nor hierarchical. So they look very, they looked at this when you might get this thing called fast scrambling, right? So one way to define, there are multiple definitions of fast scrambling, but one is that if you take a system, then you can ask how long does it take to evolve from a product state to a maximally entangled state compared with the size of the system, right? And so, and sometimes black holes, right? This is kind of one of Lenny Susskind's punchlines, right? Is that like black holes are the fastest information processors in nature, right? It's like if you throw something in a black hole, it gets spread out as Hawking radiation, right? Things are totally scrambled. And so the point is, in systems with local couplings, the spread of information is limited, right? Because the couplings are local, things have to like disseminate throughout the system, right? So to really implement this kind of log-n behavior, you need some kind of like non-local couplings, like you might see, as you might see in the SYK model, right? And so the point that this paper made was that this concept of what's near, right, has a new meaning in the hierarchical context. So yeah, it's as I mentioned, right, you must stay clear of both kinds of locality. So what they point out is that, for example, if they plot the level statistics at negative or positive S, right, then they see sort of this kind of like exponential Poisson integrable kind of distribution, right? And but to see something more like to see something that appears quite closely to fit the Wigner-Dyson distribution, right? And this is for the orthogonal ensemble, right? Then they have to sit right at the middle, S equals 0, where they are neither the regime and they have neither continuum limit. Okay, so that was their punchline. So that was some motivation they added for why it might be worthwhile to look at. And now I didn't tell you what does their proposal actually consist of, and of course it's rather than tell you how it was proposed, I think I should just tell you how was it actually done, right? And so the experiment was realized a few years after the proposal by the Monica Schleyer-Smith group at Stanford, and then so to this publication. Which indeed, references the model, right? Like mentions the inspiration coming from the model we talked about. So yeah, the rough idea now is, first of all, what are your sites? Like, how many lattice sites do you have? What are the lattice sites made of, right? So the answer is that they used rubidium 87. Okay, so rubidium is number 37 in the periodic table. So it's like, if you remember your orbitals, right, you can go through the exercise. Right, so if you fill through your if you fill the orbitals, right, so two, right, you fill them, and then eventually once you get to 37, you have a single electron left that goes in an unfilled 5s orbital. Okay. And now, so the nuclear spin of rubidium 87 is 3 halves. Okay, so the 3 halves combines with the 1/2 electron spin, right? And it splits it into a spin 2 state and a spin 1 state. And the spin 1 state has the lower energy. Okay, so the spin 1 state has has a threefold degeneracy. But then adding an external magnetic field, you induce a Zeeman splitting. So they're doing a weak field Zeeman splitting, and the level splits in 3. Okay, and what's important for our purposes is that in the weak field splitting, right, the difference from 0 to 1 and -1 is the same, right? So you have 3 energy levels that are equally spaced with the same spacing between them. And yeah, I couldn't resist. It's kind of, it was fortunate for me, right? Because apparently rubidium 87 is so standard, which I didn't realize for the Zeeman effect, that actually if you just go to Wikipedia, the Zeeman effect, they'll show you exactly rubidium 87, which is the one they looked at. So it's very easy for me. I could just take the Wikipedia figure. Yeah, so the idea is that, maybe I should clarify. So it's not that their system size, they say 16. It's not that they have 16 atoms. It's they have 16 ensembles of on the order of 10,000 atoms. Okay. And then they initialize the system in the m equals 0 state, right? You put a strong magnetic field to initialize them in m equals 0, right? And then the idea is that then they drive the optical cavity now with a position-dependent magnetic field on top of the Zeeman splitting. So the idea is that the position dependence means that they can change, they can make they introduce a gradient, right? They can have the magnetic field vary in space, right? In such a way, right, that the differences in energy level can vary from site to site, so that some will be very close to resonance and some will be off resonance compared to the driving field that can induce transitions. Right. So the idea is that some of them will be very close to resonance between each other compared to the driving field, such that you can very easily transmit energy. So like, because then you can have this position dependence in the fields, right? It means that the physical locations don't matter too much. And you can engineer things however you want. And so the way they look at, how do they compute a correlator, right? What they actually measure is that they measure the covariance, right? So they simply look at, you perform the experiment a bunch of times and then you compare them, right? Like, how correlated are the numbers of up you measure here to the number of down you measure here, right? And then ultimately they have these 16 sites. So in some sense, this is some 16 by 16 matrix where then for each point, they can then indicate how strong was the correlation between the induced spin flips at those respective sites. So here quite concretely is what the measurement looks like, right? So there's so to explain a little bit, right, that we have the top half and the bottom half, right? So in one case we have -1, this S value I showed you, right? This is them attempting to engineer S -1. That's the top half. Okay, the bottom half is S equal to 1. So let me remind you again that negative S, that's the local regime. Positive S is the hierarchical regime. Okay? And then what they show here is basically this is just plotting things, the spin sites directly, and here they plot them after performing the monomap.
So, but the S parameter in your model was the parameter we can tune, right?
That's right.
In the Hamiltonian. But now the physics of this rubidium is particles.
Yeah.
What kind of Hamiltonian is describing such system? We don't know that. Or the Hamiltonian might not be like that, right? Am I missing?
Yeah, I mean, you could say they create one that effectively looks like that, right? Where you're treating these rubidium, like you're treating these like 3M levels, right? You're treating the top and the bottom one as your S+1 and your S-1, and then the ones that are on the 0 you just ignore. So then effectively it's a C2 system, right? And then they make the position space coupling such that they approximate, such that they give the behavior we saw in the model. So for in the negative S regime, right? If you plot things in position space, you see the correlation, right? Is that like they're sitting on the diagonal as the very colored ones, right? The farther off diagonal you go, the less correlation you see. Or if you plot the correlator, it dips down, and then this is just the periodicity as I showed you, right? That it goes up again. And if you point it by the monomap, right, it just looks like a jumble, right? And it looks like you have like correlations, strong red dots everywhere. But meanwhile, if you go to the opposite limit with positive S, right? Then when you plot the correlations with a standard distance, then yeah. So again, it's periodic, right? So that's all why it's high at the low and the high ends. But then yeah, you just get a jumble when you're in the hierarchical regime, unless you perform this monomap, right? And then you start actually to get something monotonic. And you see how when you actually plot this matrix with the correlations, right? You see that you get the block sitting near the diagonal. Whereas now, if you plot them directly, they look totally messy. So in some sense, I mean, you might consider this more of a proof of concept than anything, because maybe to a disappointment that this really was all the experimental part of the talk. So there are several criticisms and objections you might have. One of them was you could say that like from a theoretical point of view, this was extremely simple, right? Just a C2, right? Like so, shouldn't we try something more fun, having like all the Pauli matrices in the game? And you can do that, at least theoretically. What would happen in this case, it turns out, is that you theoretically this is described by an admixture of the different kinds of direction. Loosely speaking, it's a how it's like when you have a quantum system, you can describe it as a statistical system in one dimension higher. Like there's the standard thing when you have like a transverse field Ising model where you can write down the transverse field as kind of taking a trace in an extra direction. The point is this trick, the extra direction is always a standard linear one. So you have some kind of tree with a transverse icing, then you perform this trick. That means now you have a hierarchical direction, and then you have a trace over a real direction. So that's why you get a mixture. And you actually can do like compute critical exponents there. And it's kind of a fun exercise where you do Feynman diagram computations, where your loop diagrams now involves both integrals and these kind of like both real integrals and tree integrals, these like kind of geometric sums. So this I won't go any more into. The other comment you might have is that it seems like this was like carefully fine-tuned, right? This seems kind of like an unnatural construction, right? So this is the next question we'll address. So now we get to this occurrence part, right, of the talk, so the second to last part. And so I couldn't resist putting this quote here. This is by Robert Dijkgraaf. So let me read it aloud to you. So, confronted with the endless number of physical systems we could fabricate out of the currently known fundamental pieces of the universe, I begin to imagine an upside-down view of physics. Instead of studying a natural phenomenon and subsequently discovering a law of nature, one could first design a new law and then reverse engineer a system that actually displays the phenomena described by the law. Right? And yeah, so
Solution in search of a problem.
Yes, that's right. Yeah, with reference to Luigi Pirandello, 6 people in search of an author. Yeah, so I couldn't resist putting it down here, but actually it's just to make the point that I don't want to rely on this perspective. Okay, I want to argue that there is actually some reason, that doesn't require you to carefully construct the things you observe. So the idea now is to present a simple lattice model with what seems like natural interactions, and then show that there actually is a limit where it behaves in the hierarchical manner. Okay, so that's what we're going to do now. So the model I want to talk about, it's defined on the hyperbolic lattice. Okay, and then the idea is if we imagine that the degrees of freedom, we can take them to be C2 value. That's not too important. But so if we have the degrees of freedom living on like the faces or the plaquettes of this lattice, okay, then there are two kind of interactions that we could imagine. Like if we just want to write down something that seems natural and local, right? So one is we could have them interact across the edges, right? The other way we could imagine is that they interact across the vertices, okay? And so here I've written down the edge interaction, and here I've written down the vertex interaction. And just to help ease my explanation, I've actually taken the sign to be alternating. So for this tessellation, it will be important for us that the number of polygons meeting at each vertex is even. But if you wanted to, you could just flip the signs of every other polygon, which would just change, then this would become a plus. So in some sense, you could absorb it into the sign of JH, at least for the cross term. But we will need this alternating sign. So that's the model we'll consider. So first you might ask, let's suppose you take the limit of the edge strength being very strong, just forget about the vertex coupling, okay? In this case, you just get the Ising model on the dual lattice. So the idea of the dual lattice, right, is if you place a vertex at every face, right, and then you have an edge, you get an edge that intersects the edges on the original one, right? Like I'm just arguing that one might see that this is the Ising model on the dual graph. But so this is a familiar model, right? So that's really not what we want, right? That one's already been studied, right? We want to see instead what happens if we take the other limit. Suppose we consider the vertex interactions to be very strong. What happens in this limit? Okay, and so the first question that's useful to answer is what are the symmetries? And you remember that basically the vertex interaction has alternating signs of these spins. So now the point is that basically you can, if you flip the sign within any of these tree wedges, right, then you have an even number of sign flips in the interaction. Right, so the Hamiltonian is not going to change, right? You can do this for any like what you might call the tree wedge. Flip all the signs within any tree wedge. So now you already begin to sort of start to see the trees appearing. But now, if you take like the strict large limit of this with a very strong vertex coupling, right, then really every vertex is just going to give you like a rigorous constraint, and you can use that constraint to eliminate some of the degrees of freedom, and then you're just left over with independent degrees of freedom. So it's kind of an uninteresting limit, right? You just get a bunch of independent C2 spin flips that do nothing. If you take the J vertex to be large and you imagine you're at some reasonable energy yourself, right? Then everything is just frozen out. You just have a very degenerate ground state. But the idea now is if you turn on this G edge, you lift this degeneracy. So what happens now is that the degrees of freedom only decouple partially, and the model actually splits into decoupled trees. So if we go back, right, originally we worked with degrees of freedom sitting on the faces, right? So suppose now we introduce some edge variables, right? And these will have to have some orientation that gives you the difference between the sets sitting on the two sides of an edge. So you need to introduce some kind of right-hand rule or something to define the sign, okay? But that you can do. So now you can think of the edge variables as being associated to trees, right? So I've drawn them two now, one in red and one in blue. And then the interaction term is the sum of the squares. So the point is, you remember the edges are the differences between the two sets. So really, for example, in this case, right, where we have 6 faces, those 6 faces, you can think of it as being 3 edges, right? That gives you the 6 terms from the differences, or the opposite 3 edges. So generically, what you would have is if you want to think in this tree language, then you have coupled trees, because the values of the sum have to agree with each other, right? It's the same sine sum of 6 face variables. But the point is that when you take this G vertex, sorry, I think about edge here, that should have been vertex. This should have been J vertex. Yeah, I'm sorry. But the point is, yeah, then in this limit, you have a rigorous constraint that you don't have an excitation here, that this sum is 0. So that means that now you can just, if you want, you could think of this as a rigorous constraint being imposed on the trees separately, because it's just saying something is 0, right? They no longer have to give the same value. They're just both giving 0. And actually, you can use this Euler formula for planar graphs, and you can see that the degrees of freedom match. So the point is, yeah, now we think of things in terms of the tree. And then we can also write these edge degrees of freedom, we can write as vertex degrees of freedom. Okay, so this is what I said, right? Without the edges, we just have a very degenerate ground state. Now we lift it, okay? And so if you take this action we have for the edges, right, which is this differences of the set variables, we can write in terms of the edge variables or in terms of the vertex variables. And then the option is that we get this graph Laplacian that we talked about. So what you get now is, in the end, the model decouples and gives you sort of an infinite set of infinite in, if you take the hyperbolic tessellation all the way, but you get a set of independent decoupled trees, each of which is described by this subroutine model that I talked about. That was kind of this ADS CFT toy model from the late 80s. Okay, and so just some comments. Yeah, to get the decoupled trees, you really do have to take G vertex to be infinite, or at least the temperature has to be much lower. But you can work it out sort of perturbatively. You can introduce, the next correction would be looking at the couplings between pairs of trees, right? And then next on, you would have like 2 trees coupling with each other or 3 coupling together. So you could work out an expansion that corrects this tree picture. And then this subordinate model, I mentioned it has this duality, right? But the dual model that sits on the boundary, right? These decoupled trees are totally scrambled together. So at least if you go into this blind, it would be very hard to see that you had a boundary theory corresponding to your bulk theory, because it's all meshed together, scrambled on the boundary. And then you can introduce a notion of lattice models, and you can actually see they behave kind of like, in some sense, kind of like toy model BTC black holes, in the sense that you can sort of see you get this kind of boundary kind of behavior, like the boundary with the black hole will give you sort of extra degrees of freedom. In the sense, right, constraints are coming from the vertex. So the point is that once if you introduce a holonomy to your graph, right, then you could say that the ratio between your degrees of freedom and your constraints is lowered a bit, so you can have degrees of freedom that run around this circle, right? And that's where you can see this kind of toy model behavior. So let me just mention that there was this kind of follow-up paper by one of the authors from the original paper, which then kind of argued how you can get this entanglement entropy that sort of follows what you would have expected from a boundary law. So yeah, just a little high energy aside. But with that, I really do want to move on to the last part of the talk, which is speculating about the UV completion, right? So the point is, I was talking about continuum limits, I was talking about the effective low energy physics, the kind of thing you see when you flow deep in the IR and doing renormalization, group flow analysis. So what about the high energy physics, right? So this last part, this is ongoing work. So this is you could say the applicability is very skeptical. Feel free to weigh any kind of criticism and comments. I would love to hear about them. But also, there is a fun story that I think is worth presenting today. Okay, so you could say that this is something that like string theory is talking about a lot, is whether string theory is the only UV completion or not. Ultimately, the way that string theory combines together Lorentz invariance and unitarity is highly non-trivial. Like the point is that if you're doing quantum field theory, right, basically whenever you try to introduce a regulator, it always violates one of your sacred principles, right? It's like, if you do Dimweg, strictly speaking, Dimweg is, your theory becomes non-unitary. You have these evanescent operators with complex scaling dimension, if you try to take it literally, right? Or if you use Pauli Villars, then you're modifying the propagator in a way that if you take it literally, either you introduce extra wrong spin particles, or your correlator, if you think of it as modifying the propagator of one particle, you kind of have a non-local correlator. Like basically all the standard regulators will break some principle or other. But okay, I'm not in any way trying to say something as ambitious as to finding something regulator free, right? Like we really, all we're gonna do now is we're gonna look at the kind of like towers of states you might get in the hierarchical setting, and see how, if we can find some analogy to the way that strings behave sort of in the healthy thermodynamic manner. Okay. So let me just briefly start with a review of the string theory story, which again, this is just simple, it's non-relativistic string theory. So I'm not going to say anything in advance. I trust everyone actually will be able to follow this part. So the point is, if we just, so let's make it even simpler. Let's just take a classical string, okay? If we take a classical string, right, we can write down, Newton's equation of motion, right? And we're taking a limit of like small, take a string. It can either have Dirichlet or boundary conditions, right? You can attach the endpoints, or you can have them sit on some hoops that can move up and down. Okay, and so now if you're trying to find the normal modes of the string, right, you can solve them either with Dirichlet or Neumann conditions. This is just solving a classical equation of motion. It's not too hard. In either case, you get this integer spectrum of normal modes, right? This is, I mean, of course, this is very familiar, right? Like Pythagoras knew this, right? You put a string in two edges, you get this infinite tower of normal modes with more and more wobbles on it. Okay, and you can also you could instead apply periodic boundary conditions, and again you get the integer spectrum, which is just saying that these the kind of eigenfunctions, the complex exponentials, if they sit on the circle, you have an they're integer labeled. Okay, so nothing advanced here, but now let's make it slightly more advanced. Let's go to quantum mechanics, right? So the quantum mechanics idea then is that you think of each of these normal modes as being a quantum harmonic oscillator, right? And the harmonic oscillator, has this infinite tower of integer-spaced energies, right? So really what it means that the string spectrum, once we go into the quantum mechanical theory, is built from an infinite set of oscillators with integer-spaced energy quanta, okay? So we have an infinite set of oscillators, and each oscillator itself has an infinite tower of energies. Okay? And now let me just introduce this notation here, okay? So let's just for now ignore the 0-point energy. I'll comment on it again later. What I mean is, the quantum harmonic oscillator, right? It's n plus 1/2, right? There's this extra 1/2 sitting there, which I'll talk about briefly, but let's just ignore it for now. So this is the partition function you get, right? You get a product. This product that goes k equals 1 to infinity is the product over the independent harmonic oscillators. And then you have a sum for each harmonic oscillator over all the excitations of any one given oscillator, right? So if you just evaluate the sum, you get this infinite product. Now this product here, this infinite product here, is actually, you can write it down in a closed form in terms of a function mathematicians have defined, namely the Dedekind eta function. Okay, so this is the exact value for the partition function. Okay, and from the partition function we can get the free energy, right? And now this was something fun, which I think not so many expositions would include if you look at the places that review the non-relativistic string. But actually, there is a formula you can find. There is a mathematical formula that gives you the logarithm of the Dedekind eta function. The upshot is that if we want to look at like the high temperature behavior, okay, then you actually can work out. You can work out an expansion, but you can actually work it out to all orders, including sort of non-perturbative corrections where beta sits in the denominator. So this is just an exact mathematical identity for the entropy that you get for this system. So now, to get the density of states at high temperature, you can perform a saddle point approximation. This is quite a standard technique. This is the formula where you use you plug in the solution to the saddle point equation that you get from differentiating the entropy once, right? So this, like at large energies, this is the approximation. So you just plug this into this formula, and then this is the formula you find for the density of states. Okay, and for those who are into number theory, right, they might recognize that actually what you get here, this is kind of the physics derivation of the Hardy-Ramanujan formula. So I'll talk a bit more about that on the next slide. But let me just, before I go to the next slide, to say, like, we take the logarithm, right? So we take the logarithm of the density of states, of the number of microstates. That gives us the entropy, as we know from Boltzmann's tombstone. So really you just get what's sitting inside the exponent, a leading order, okay? And this is, this is the kind of behavior we want from a physical system, right? We want the entropy to scale as the square root of energy. This is like the behavior of standard two-dimensional system. And my point is just that from the string, this comes about slightly non-trivial. So this is this Hardy-Ramanujan, right? But the point is that you could compute the entropy exactly, not use like for any given value, you could compute the exact density of state just from the integer partition, right? Because the point is we have these infinite harmonic oscillators with more and more energy, and they can be excited any number of times. So ultimately, the degeneracy is just the numbers of ways you can add natural numbers together to get a given number, right? This is what mathematicians call the integer partition, right? And you can work it out exactly. And then this is, so this was a pure math result, right, by Hardy-Ramanujan for how this function behaves asymptotically when n is large. And actually, if you look at their proof is much more complicated than this simple saddle point approximation. So the physicist way of deriving is very fast. Although to be fair, they had an expansion formula for higher order terms as well, which though you could work out with from the thermodynamic, from the physics approach. And so ultimately, so the fact that we get this entropy that scales as square root t follows from this number theory, the fact that's maybe like slightly non-trivial that this integer function has this behavior with exponential square root n. So ultimately, our goal now for this last part of the talk is if we can find sort of from the hierarchical context, if we can reproduce this behavior. So if we can get some deformed integer partitions that has Hardy-Ramanujan type behavior, that's going to be our goal. Okay, and now, some comments. First of all, this was oscillations in one direction. I just took one transverse direction, right? In what you ultimately end up doing in string theory, right, is that you have multiple transverse directions, 24 to be exact, right? That to leading order, the correction is very simple. You just have a square root of number of transverse directions. The other thing is, as I mentioned, this is the non-relativistic string, right? So if you instead use relativistic dispersion, right, then it's not the energy that has the integer spacing, rather it's the energy squared. That's to say because I'm not looking at I'm only concerned with the oscillation modes, right? If you want to see this Hagen momentum, there's also an overall momentum you could bestow on the string, right? We're just looking right now at like a stationary string and its excitations. So the point is, my point about the relativistic spectrum is that if you remember the Veneziano amplitude, these string theory amplitudes, they have a tower of poles, right? And the tower of poles is integer spaced in Mandelstam invariants. Right, the Mandelstam invariants are not momenta; they're squares of momenta. Right, I'm saying this. We see the integer spectrum in the energy, not energy squared, because we're working non-relativistically. And then there's this comment about the 0-point energy. Right, really, you should include this factor of 1/2 for all the oscillators, and of course that's divergent. Incidentally, though, if you regulate it with theta function regularization, and you have this factor of 24 from the 24 transverse dimensions in bosonic string theory, you actually do get precisely -1. That's to say the offset you have for the tachyon, right? That you have one tachyon and then a massless state and so on in string theory. So those are some comments. Now we will move on to the hierarchical case. Okay? And so here's a quite important comment to make was that when we were working with a string, the boundary conditions didn't really matter much. We always got an integer spectrum. It turns out for the tree, the boundary conditions matter a lot. You get a totally different answer depending on the boundary conditions, and it's not too hard to understand why. I mean, the point is, if you think of a string, if you try to discretize the string and think of it as a graph, right, then you have a sequence of points and you just have 2 boundary points. So if you have a very large system, the fraction of boundary points tends to 0. Okay? But for a tree, you can see the boundary points grow exponentially. So actually, you have some finite fraction of the points are boundary points, even in the large system limit. Okay, so that's why the boundary conditions really do matter a lot. So let's consider the options. So the first option is we impose Dirichlet conditions. So right here, these equations are just the string, and this is string I'm plotting to the left, right? If you have a p plus 1 regular graph, that's a 2 regular graph, right? That's really just a chain. Every vertex in a chain has 2 neighbors. Okay, and so now so the point is, it's simple enough, the system, you can solve it exactly and find what are the normal mode frequencies, right? I didn't put anything on the x-axis because these are just, these are just different values of normal mode values you can get when you try to solve the equation of motion. But the point then is if you take the limit where the system becomes large, keeping the total length of the string fixed and the total mass fixed, you get the integer spectrum we had earlier. So that's just saying that this curve, right, if you take the number of points to be very large and you zoom in here, right, then this is plotting the square, right, and this itself is a parabola. So taking the square root, we get the linear behavior, and all this part just gets pushed off to infinity when we take the large system limit. But if you try it out with the tree graph, it becomes gapped. So the point is, if you take the large system size limit where you get a finite distance between energy levels, then everything gets pushed off to infinity. Okay, so that's really not the interesting regime, right? There's no way we can get like Hierarchical type behavior, give us healthy thermodynamics in this case. So let's move on to non-end conditions. The non-end boundary conditions are a bit more interesting. So what happens here is actually, right now I'm plotting it for the tree with cluster size 7. So that's the 8 regular tree. So plotting now here the normal mode frequencies, and then actually it turns out there's a degeneracy this time, something that didn't happen for the string. That's to say you have multiple independent oscillation modes with the same normal mode frequencies. And so here I'm plotting, this is the degeneracy. I've divided out a factor just because otherwise I'd have to include it all these places. But so the point is you have a bunch of normal mode frequencies sitting up here, and then actually you have some extra ones that sit very, very close to 0. And what actually happens when you take this infinite system size limit is that this whole top part gets pushed off to infinity. And this part here actually will be the one that gives you a finite set of energy oscillators. And it actually turns out that the square of the energy, this function here, is just an exponentially growing function. So instead of the integer spectrum, we get an exponential spectrum. Okay? And an exponential spectrum with degeneracies. So the higher normal values, normal frequency have bigger and bigger degeneracies. Okay, so I'm not going to dwell too much on this. This has some features that we'll recover, but turns out this is not the answer. This will not give us, the right sort of Hardy-Ramanujan behavior. And already one feature you can see is that if we want P to be generic, if we don't assume that P is a square, right, then the energy levels, once we take omega itself instead of omega square, so the normal mode frequencies, which, multiplying by h bar gives us the energies, right? The energies follows, exponential, but taking a square root. So my point is that you don't get degeneracies, right? If P is not a square, right? If you take the square root of some exponentially growing numbers, right? Generically, you get a bunch of irrational numbers, right? That are not going to produce degeneracies. So we don't quite have the right answer. Then you might ask, what about periodic boundary conditions? Could we impose those? And the short answer is sometimes you can. So here's an example of a finite tree, right? So in this case, we have many boundary points, as you can see, right? So it seems like, what do we mean by periodic boundary condition, right? Like the string has just 2 boundary points. We identify them. Now there are multiple points, so there are multiple ways to identify them. So what is the right way of doing it? And at least I would say that any sensible way of doing it should respect translational invariance. In graph theory language, this translates into you want a vertex transitive graph, right? You want every vertex to be identical to every other, right? You don't want any vertices standing out. And turns out this can be done in some cases for some graphs. And actually, several of them are known. So this one, the Hewood graph. And more generally, any graph, anytime you can perform this kind of boundary identification to get a vertex transitive graph, what you get is called a Moore graph. These graphs have actually been classified by mathematicians. And the upshot is that the only cluster size for which you can perform Moore graphs for any size of a graph is when P is 1. That's to say the chain. So the string is actually the only infinite family of Moore graphs you can create. So, okay, so that can't quite be the answer. So let's move on. So then the final proposal, which is actually going to be the one that turns out to work, it's slightly more sophisticated, so I can't quite justify it to a level that would maybe satisfy the physicist audience, because it's built on a sort of more abstract mathematical argument. So the point is that we want to think instead of like these other pictures where we think instead of a tree to have some fractal, right? Really what you would have is some fractal propagating in space-time. So the different approach you might have is to say that rather we want to look at some familiar world sheet using this ultrametric notion of distance. So it's more like looking at the familiar world sheet with a different distance, with the different notions of distance. But then, to determine the spectrum under this perspective, right? Then let's just compare. So with the usual case, right? We have the periodic boundary conditions come from you take the circle, which is the set of numbers with a unit norm. Okay. That set you can also define with respect to this hierarchical distance. You can define numbers with unit norm. Okay. And now the exponentials give you the full set of what are called additive characters, right? That just means that if you multiply 2 of them together, then the arguments just add up, right? You get the same function with the arguments added up. So I mean, this is also the function you use when you Fourier transform, right? So in general, this is like the set of characters you can define on the space. And then the values we got for the normal modes are the eigenvalues of this operator when acted on with the differential operator. So all these things have an analogy in this hierarchical setting. Okay? The upshot is that you can do this, and you can derive some set of values for each of these norms. And to show it explicitly, you have to carry out an integral over these tree norms, which I thought I'd spare you. So let me just show you the answer in the case. So let's just, for simplicity, take a concrete case, the 2 cluster size case. So it turns out that if you look at these characters that you can define on this twofold ultrametric circle, then their eigenvalues are given by this function here. Okay. So 3 times 2 to the n minus 1, and then there's some dimensional factor that you can't determine just from mathematical consideration, right? So this is the dimensional fold parameter, right, that carries units of energy. So again, we get an exponential spread of energy levels like we had in the Neumann case, but now it's actually the energies themselves, right, rather than their square that has the exponential behavior. Moreover, there's this offset term. And finally, you also, like in the Neumann case, you get an operator degeneracy. So this is just the end. This is like a mathematical fact that you get this if you look at these characters on this twofold circle. Okay? And so now the point is, you have this larger spacing, right? The spacing grows exponentially. Ultimately, you would expect that to lower the entropy, right? It's like if you're constructing degeneracies, the different oscillators you have to build them out of, your Lego pieces are spaced farther apart, right? So you should have fewer ways of assembling them. But there's a canceling effect because you also have multiple, at any given level, right? There's multiple different oscillators with the same energy quanta. Okay, so the question is, how does this behave compare to this S square root E behavior? Okay, and so you can write down the partition function, and so it's like before, right? For every oscillator, we have to sum, right? So we still have a sum over integer spacings for any one oscillator, right? That's still just the standard harmonic oscillator. And then we have a power because we have a degeneracy, right? So that just gives us E for the degeneracy. We just get a factor for each oscillator with the same oscillation mode, and then we have a product running over all the different the normal mode frequencies. Okay, so again, you can carry out the sum, and you get this form, and now I'm just writing things out explicitly. So this is the partition function in this case. Okay, and then we can get the free energy. Okay, so it's slightly different from before. What's the high energy behavior, right? We want to ultimately perform this saddle point approximation again. And the short answer is that just like in the usual string, you do get this energy behavior that goes as 1 over beta squared, which is indeed what you would want for a 2-dimensional system, right? This is free energy density, really, right? So it should scale with a number of dimensions. So again, we're starting to see this 2-dimensional behavior. A slight difference though is that unlike the string case, you actually, if you square the free energy density by beta squared, you don't get a finite limit. You actually get a limit set. You get some oscillations that are oscillatory in the logarithm of beta. And then this is not a new fact. If you look at, physicists have looked at these trees, or also sometimes called the Bethes lattice before, and log periodic oscillations do appear. Okay, so the more precise formula is more involved, right? And involves, I've written here in terms of complex numbers, but you sum minus and plus. So it is a real answer. Okay, let me just use an overline to show when I'm washing out, averaging over these fluctuations. Okay. So again, we can use this leading behavior at high energy, and we can perform a saddle point approximation. So let me just again remind you, this is the standard non-relativistic string, right? This is the Hardy-Ramanujan behavior, right? Is this, you have some power of E exponential against square root E, right? With some coefficient here, and the power of E sitting in front of the exponent being 1. Here's what we get when we average out over these fluctuations in the base 2 case. Okay. So you really do get this square root E behavior. The coefficient is slightly different, but it anyhow depends on this, your unit in front of energy. So this is not really a universal quantity. And then the number you get for the energy, it's no longer 1. It's some number very close to 1. But the leading behavior is, again, we take the logarithm, we get the entropy, again has the square root E behavior that we wanted. So that's sort of the upshot. And let me, I couldn't resist. Let me just show you concretely how this works, right? This is sort of, I feel like when you do this thermodynamically, it seems trivially, but if you actually try to compute the microstates exactly, it feels non-trivial. So let me just show you explicitly, right? This I told you were the energy oscillators and their degeneracies in the 2 cluster size case, right? So you have basically the first energy here is 2 in the units I'm using. I said this epsilon not equal to 1. So you have 2 and there's just a single oscillator, right? Then you have 5 and you have 2 oscillators, 11, there are 4, and so on. One, for example, you can construct 1, right? You can't sum these numbers to get 1. You can get 2, you can only get that one way. If we keep going, once we reach 4, there's still only one way of doing it. We add 2 twice. But suppose we go to 5, right? Then we have 2 different oscillators with 5 energy. That gives us the twofold degeneracy. And if we go higher to 10, for example, then we can add 2 together 5 times, or we can add the 2 different 5s in 3 ways, giving us the total 4 ways. So if you do this counting problem and you do it higher and higher, right? Like if we had taken this as our starting point, then probably this behavior would have been less trivial, right? But the point is that this again has the kind of Hardy-Riemann type behavior with the square root n. And even in this language, you can actually understand why there are why we take this, why there are these log period oscillations, right? Because you can see, for example, once the energy we're considering passes one of these values, right? Then suddenly we get many more ways of building the number, since then we can use all the building blocks in the given energy level we pass. Okay, and yeah, so I showed you the cluster size 2, but you can work this out for the other cluster sizes as well, right? Here's the general formula for the energy of the individual oscillators, and here are the degeneracies, and again, you get the square root E type behavior. Okay, there are some other parameters, they depend on P, but that's the behavior. And yeah, okay, and let me just show, so the comparison. The main point is if you actually plot so if you look at the degeneracies, right, you see that they follow each other fairly closely. It's almost hard to plot unless you take the logarithm. If you take the logarithm, then it's literally the entropy. And you see the 3 curves, whether you include the oscillations or not, it's very hard to see. They look almost completely overlapping. It's a bit easier if you take their ratios, right? Now you can see, so the green one is using the saddle point approximation, but not washing out, like taking into account these log periodic oscillations I mentioned. Whereas, so overline is without taking them into account. So that's why the overlying one oscillates about the asymptotic value, whereas the sort of true saddle point approximation goes straight towards 1. So my comments are here. So let me mention that because my own background sometimes is I've also worked quite a lot in this sort of S matrix bootstrap community. And there, a big question people often ask is if there exists some kind of Q deformation of string theory or string theory amplitude. So people were trying to find like Q deformations of the Veneziano amplitude. And the, string theory might very well be the unique answer, but if there really is this kind of Q deformation, then I think arguably these kind of behavior we've seen, where you get the exponential behavior and the degeneracy, I think would be the most likely candidate. And then there were these long periodic fluctuations. It is possible that they ultimately indicate a sickness, that like an insurmountable obstacle to actually seeing these kind of systems in nature or in a lab. It's possible, but let me just point out that the oscillations are not so large, right? Like, the oscillations, of course, go up and down, but they multiply the free energy that has the overall envelope, right? This overall 1 over beta squared envelope. So my point is that if you look at the free energy, or if you look at the entropy, it is a monotonic function still, right? Like there are fluctuations, but they're not strong enough to overcome the monotonic behavior of the envelope that it multiplies. And now, so I'm just clarifying, the main reason why I felt this sort of ongoing work interesting enough to all subject you to this, at the very end of a Friday, it's just the fact that this spectrum, which came about for some abstract number theoretic considerations, right? Like the spectrum wasn't engineered by hand or tuned in with factors and degeneracies to work it out, right? This is directly what you get from looking at these characters on this hierarchical circle, right? And they do have this balancing that gives you this right square root E behavior. And then again, I omitted the 0-point energy, right? What if we include the 1/2 from all the oscillators? So that's what I'm doing here, right? So this is basically this value, this is the energy, and this is the degeneracy, right? So because the formula for the degeneracy is slightly different from the first case, from the higher case, it's written as 2 terms. But basically the point is, if you sum over all the oscillators and you sum over their contribution from 1/2, of course it diverges like it does in the other string. It needs regulating. But in this case, there's an obvious regulator, right? Which is just geometric series, right? Like a geometric series that diverges, you just use the answer for the geometric series, even though it only converges, right? When the argument is less than 1. But the point is, you somehow get exactly 0, which seems sort of serendipitous. All right, so with that, yeah, we've reached the conclusion, right? So basically, here's the sort of super brief upshot of the different facets we've witnessed today, right? So that there is this special kind of symmetry. In addition to the linear one, we have the hierarchical one, right? And they have been custom engineered in our lab. They can appear as sort of limits of more broad, generic, more natural systems. They have their own versions of CFT, string theory, and holography, and you know, not so much is known on this subject at present. And with that, yeah, thank you so much for listening.